Right. So, hello everybody. Bonjour à toutes. Thank you for joining this lunchtime seminar organized by Young SECED and the Group Jeune de la FPS. Today's talk is about earthquake risk modeling. There are three great speakers who will provide some insights in the recent research advances from both the UK and France. Before moving on to the talk, there are a few housekeeping rules to go over. So please can all guests keep their videos off and microphones on mute during the seminar. We're going to have a Q&A session after all presentations, but please feel free to type your questions in the chat at any point. And please note that the seminar is now being recorded and will be uploaded onto the SECED YouTube channel. So by dialing into the event, you consent that any views or opinions you share are being made public. So first, let me introduce myself. I'm Marco Baiguera. I'm the current chair of the SECED Young Members Committee, and I'm co-chairing today's seminar with Reine, chair of the group Jeune de la FPS. It's the first time for the two groups to have organized a joint seminar, so we would like to take the opportunity to give a very short introduction about our societies. So I'll start first. So SECED is the Society for Earthquake Engineering and Civil Engineering Dynamics. It's the main forum in the UK for people coming from both industry and academia who have an interest in earthquake, blast, and other types of dynamic effects. Within SECED, members under the age of 35 are represented by the Young SECED Members Committee. Currently, there are 12 committee members who dedicate their time to organize a mix of activities directed to the young members, such as this lunchtime seminar, the annual SECED fund, and for instance, site visits, such as the very recent one that took place on Tuesday at the HR Walling for the tsunami simulator, which is the largest specialist tsunami facility in Europe. So I also would like to let you know about two important upcoming events organized by SECED this year. The Mallet Milne Lecture, which is the most significant event organized by the Society every 2 years. And the 18th lecture is given by Alain Pecker, a professor à l'École des Ponts et Chaussées, and so well known to many of you. We will give a lecture on the interrelationship between practice, standardization, and innovation in earthquake engineering. So that's going to take place on the 31st of May at the Institution of Civil Engineers in Westminster, London. And finally, our 2023 conference in September in Cambridge. So the title is Earthquake Engineering and Dynamics for a Sustainable Future. So please stay tuned for many other events organized through by SECED through our social media channels. And now it's Ren's turn to introduce the FPS. So you can now share your screen.
Thank you, Marco. So I will share the whole screen. Let me know if you can see my screen.
Yeah, perfect.
So perfect. So first of all, I would like to thank Marco for reaching out, and I'm so happy to be with you today and to be representing IFPS and presenting our activities. Well, we're the equivalent of SECED in France. Of course, I cannot talk a lot about the IFPS. I will only give you a glimpse of what we do. So the IFPS has around 450 members, and there's a whole team behind this society. So here I show you like the board, the scientific committee, and the other branches of the IFPS. The youth committee is one of these branches. So I mention only the names of the chairs and well, person in charge, but as you may know, you may imagine, there's a whole team behind these people and these groups, and well, they are all thankful and well deserved to be mentioned. So to present for you the youth IFPS, so here's our heads, as you can see. So our 6 member of the committee, but we are 62 members, so we have the same requirements to join the youth IFPS. So you need to have less than 35 years old, and you need to be a member of the IFPS. So we have a lot of activities. The seminar is one, the web seminar is one of them. We have technical days. So here you can see an image of the technical day that we've done in Nice. And you have technical visits, scientific reach out, and working groups. So I wanted to take a few moments just to present 2 activities of the IFPS. So one of them is the IFPS post-seismic surveys. So it's all in the title. So it's surveys that we do, mission that we do after an earthquake, a major earthquake normally. So the first one that was done in the IFPS was in Mexico, and after the earthquake of the 1985. And after that, the IFPS has organized more than 41 survey and all around the world. So what I would like to mention that now we are preparing for a survey in Turkey after the earthquake of the 6th February. So we have this group that is working virtually on preparing this mission to be able to do a mission soon physically in Turkey. Another event coming is the next symposium. So it's entitled Seismic Risk and Multi-Hazard. Why multi-hazard? Because we're going to organize it in Guadeloupe this year. So Guadeloupe is a French isle in the Caribbean Sea. So it's going to be held from the 7th to the 10th of November 2023. So you can participate, everyone, because the language will be between French and English. So you can participate. You can either scan the QR code or join the website to know more. So finally, I will just leave the contact if you want to contact us. So the first email is for the youth group, and then there's the website, there's the LinkedIn, so you can be tuned to our newest event, and there's the secretarial information. So thank you, Marco. That will be it for me.
That's great, Reine. And now moving on to the talk, I'm very pleased today to have Professor Carmine Galasso, who will provide as a short introduction to the topic of earthquake risk modeling. This will be followed by the presentations of 2 brilliant young researchers, Dr. Filippo Gatti and Dr. Gemma Cremen. So our first speaker is Carmine Galasso, Professor of Catastrophe Risk Engineering at the University College London. His research focuses on developing and applying probabilistic and statistical methods and computational digital tools for catastrophe risk modeling and disaster risk reduction. Is investigating risks to building portfolios and infrastructure exposed to multiple natural hazards, including earthquakes, strong wind, and flooding, with particular emphasis on low-income countries and community-based infrastructure. So without further delay, I will hand over to Carmine for his presentation. Thanks.
Great. Thanks a lot, Marco and Reine, for having me today, despite not meeting the requirement of being less than 35. I'm saying how far away I'm from that. So I'm going to share my screen, and can you see it in presentation mode?
That's perfect.
Great. So I'll try to be short so that the most interesting talks by Gemma and Filippo can get the right time that they deserve. So I'm going today to introduce some of the ongoing challenges in catastrophe risk modeling. I know this talk today's seminar is focused around earthquake risk, but I'm going to provide some general discussion around not necessarily just seismic hazard, but also other type of natural hazards. You'll see a lot of QR codes and little photos of collaborators and the QR codes to papers that will go more in detail on some of the topics I'm going to discuss. I guess I was looking at the list of participants. I was quite intimidated. I mean, I guess many of you can actually lecture on what catastrophe risk modeling is. So I'm not going in detail here, but I guess just for people that may not be super familiar, the idea is that if we are interested in computing risk for a given infrastructure, building, or a given region, or a given country as well, what we do, we break down our task in a number of subcomponents. So typically we start what we call the exposure, where we are going to provide an inventory of assets at risk, what type of buildings we have, their value, that's very important, the replacement value, so how much would cost to replace that asset at that location, and of course a number of features of those assets so that we can classify them in a number of typologies for convenience. So because of course the actual building stock or the actual infrastructure stock in a place can be extremely varied, so we want to make sure that we can use a number of classes of typologies where we can simplify our job. So for each location where we have exposure, then we do have a hazard component, and Filippo will show some of the exciting work he's doing with this group, where essentially we are interested in understanding potential scenarios in case of earthquake, for instance, for a given time frame, what are the potential events in terms of their magnitude, fault rupture characteristics, for instance, but we also want to translate those event characteristics to local intensities in terms of ground shaking, for instance, at locations where we have asset at risk, so where we have exposure. And in parallel, for each of those typology in our exposure portfolio, we also define some vulnerability model that essentially give us the probability of damage or any other type of impact given the intensity of the hazard as estimated by the hazard components. Then we bring all together to compute some sort of risk metrics, some sort of consequence metrics. I will use those three words actually, consequence, impact, and risk metrics in my talk. And essentially, typically what we do, for instance, we quantify risk in terms of economic losses. And I'll go back to that in a few minutes to discuss why this is particularly convenient, but also what are the limitations when you use economic losses. One thing I want to point out that typically the current approach to risk modeling is a very top-down approach in a sense that there are risk modelers that develop those models. Often users at the bottom, they say that those models are black boxes. They cannot really, in some cases, be challenging to understand what is going on within the model. And typically those models, the outputs from those models are used for making decisions. Again, unfortunately, often in a very top-down approach. And typically those type of decisions are, for instance, in terms of policies, we can have corrective risk management policies. For instance, we can decide to upgrade our existing assets if the vulnerability and hence the risk is too high. We can relocate in some cases some settlement. That's particularly, for instance, in the case of flood, if we have assets in the floodplain. But we can also transfer the risk, for instance, to the reinsurance, insurance, or insurance market. So in that case, we talk about compensatory risk management policies, or for instance, in terms of some sort of social measures that we can provide. Now, there are a number of challenges, a number of limitations, and the two talks later will try to show how we can address some of those limitations when we look at existing risk modeling approaches. So I'm going to quickly work through some of those. And the first one is really this idea that current risk models, they focus on existing exposure vulnerability. So they take a snapshot of what is the exposure, so the asset at risk in a given time, Typically, for instance, we look at the latest census, and then we develop our risk modeling framework to make decisions that possibly will have an impact in the future, but really using this very static exposure and vulnerability representation of our assets at risk. And also the other limitation is that most of those models, they focus pretty much just on physical exposure and vulnerability, so assets, not much on people that, for instance, use those infrastructure systems, they live in those buildings and so on. But of course, that has a number of limitations because, and again, for earthquake is less relevant, maybe what the implication, for instance, of climate change in terms of making some of the natural hazards like flooding more frequent and more intense. But some of the changes that affect exposure vulnerability are actually very relevant also for earthquake risk. So for instance, we know there is population increase. That's particularly in the global south. So it's been estimated that there will be 2 billion new citizens in the global south in the next 30 years by 2050. That has been estimated by United Nations and a number of other agencies. And also most of those, so 95% of those new citizens will be urban. So there is a rapid urbanization, particularly again in the global south, in low-income countries. And of course, in parallel, there are, in some cases, some planned new infrastructure system, but in some cases, they are more informal. Those new infrastructure systems and those new assets will coexist with existing structure that, of course, are aging. And in some cases, there is structural deterioration. On the other side, of course, we can also implement some infrastructure adaptation or more in general retrofit, for instance. And again, you'll see, as I say, there are a number of QR codes to publications. So for instance, in this publication, Gemma and I have been discussing a bit more in detail some of those issues. So what is important when you are looking at future risk. But we also did something else. So looking at the case study of Nepal, and Nepal is quite interesting because it's one of the fastest urbanizing country in the world. So it's been ranked number 10 and is also one of the country possibly most exposed to some of the natural hazards, including earthquake. So with Carlos, one of the PhD students working with Gemma and myself, so Carlos developed a urban growth modeling, and there are various options for that. We use in particular a cellular automata model called SLEOT from the it's an acronym for the components that this model use. So essentially what this model does, it looks at historical maps and data to try to estimate future land use. And so essentially by running this model, again, in the next slide, you'll see the link to the publication. What we can do, we can estimate over time, for instance, what will be for the Kathmandu Valley in Nepal, what is going to be the expansion of urban areas. So you have the existing built-up areas in 2018. That is the year of the last input that we use in calibrating our model. But then we have been projecting and estimating future urban areas in the next 10, 20, 30 years. And of course, you can see that again, if I would build a risk model for Nepal, for Kathmandu Valley in particular today, I would possibly focus only on the blue part because it's what I get in my exposure component of risk. But that means that I'm missing a lot. In particular, here has been estimated based on Carlos' model. And again, there are several other models, for instance, by the Global Earthquake Model, GEM Foundation for other parts of the world using similar tools or slightly different approaches, but really give the same output. So there is a huge increase in built-up areas, huge increase in exposure, but really our current risk model don't really capture that. And with Carlos, we also push this a bit further. Again, I'm going fast here, but the idea, then what happens if we subject this future expansion to a scenario earthquake, a 7.8 magnitude that is some sort of replicating the Gorka 2015 earthquake. And I also look at different exposure and vulnerability scenarios today in the present, but also in the future. Some of them are essentially like a business as usual, where I don't have any disaster risk reduction action. And of course, because the urban areas are increasing, that means if I move from scenario A to scenario C, which are again the no disaster risk reduction actions, but in 2031, there will be much more urban area. Of course, I will have an increase in economic losses. But of course, what I can do, and that's a unique opportunity that we have today. So today, we have the opportunity because most of those new assets and infrastructure system have not yet been built. By design, we can make those future assets safer, more resilient, and even more sustainable in some cases. So really the idea is that, we want to look at risk in the future, not just look at risk today. And another interesting aspect, and again, we'll go back to that in a few minutes, is also that, it's interesting also to understand how disasters in general, and in this case, earthquakes, may affect different sectors of societies in different ways. So if we disaggregate, for instance, losses for different income classes, so different gender, different ages, you will see that, the impact on some of those sectors of society is not equal. And I'll go back to this in a second. In fact, the next limitation that is the one that I'm the most excited about when, for some of the work we are doing is really that I mentioned a few times that we use economic losses. It's great. Everyone can understand economic losses. Everybody can make decisions when we look at economic losses. But then I have a quiz here. So if let's say I'm a decision maker, I want to build a new coastal protection. and I have two projects. I can choose between project A and project B. They cost the same because I'm building exactly the same coastal protection. Then I run my catastrophe risk model. Of course, in this case, it's not for earthquake, it's for coastal flooding. And I can estimate that, for instance, project A, by running my catastrophe risk model with or without my coastal protection, will prevent on average 20 million of losses per year. I'll do the same for project B. In this case, the benefit is much lower. It's only 5 million. So I don't need to be I guess I don't need to be a catastrophe risk modeler to say, which one is more convenient. And of course, if we use purely economic losses to do that, of course, everyone say project A is much more convenient because, of course, the ratio between cost and benefit is much higher. However, if I go to see what is behind project A and project B, I may have that, in project A, I have few very expensive houses, maybe somewhere in Southern California, in Beverly Hills, that of course have a big replacement value. Remember at the very start, I say in our exposure database, we have replacement value for each asset. While in the second case, I may have a low income region with many informal settlements that have very low replacement value, very low economic value. So they don't really appear in my loss calculation, but of course you can imagine the impact on people if there is a disaster, a coastal flood in this case, or even an earthquake in some of those regions can be much more devastating than in case A. So long story short, we need to make sure also that, again, if you look at the future of risk modeling, we start using risk metrics or consequence metrics which are more equitable or more people-centered. So again, with Gemma and Nicole, here we are doing a lot of work, and I know Gemma, I saw Gemma in the chat, so I hope I'll give justice to your work and Nicole as well. So what we are trying to do, for instance, is to use displacement, people displacement, as a way to quantify the impact of disasters. So we start with an earthquake scenario, we look at physical damage in terms of infrastructure, network, homes, housing, and workplaces, and then the idea is, what will be the impact on people? In some cases, people will be forced to displace, and that's what Nicole is working on with, I have to say, support from the Willis Research Network. Or in the case of Gemma, is more looking, for instance, at data-driven type of models to estimate the voluntary decision of households to relocate. And again, there is no time to go in detail, but that's very interesting because, for instance, using data from Nepal, and particularly after the 2015 earthquake and household surveys, Gemma has built a data-driven model where you look at different characteristics of households in terms, for instance, of their age, what has been the impact on their livelihood by the earthquake, but also, of course, residential damage, because residential damage, and this is what Nicole is investigated, usually is used as the main proxy for displacement, for household displacement. And so really the idea is to calibrate those type of models and then use those type of models to design policies in the same way we were discussing policy before, like building retrofit. We can have other type of policies, including soft policies in terms, for instance, of financial benefits that can help people in mitigating the effect of either forced displacement or even the decision of relocating somewhere else. Of course, when you do this type of modeling and those type of impact metrics, I'm going fast here, but you cannot look at building in isolation. That's another limitation of what current catastrophe risk models do. They pretty much look at building in isolation, pretty much mainly residential building, commercial, industrial. But of course, we need to have we need to look at our exposure in terms of system level thinking, where essentially there are buildings, but what really matters is also disruption, for instance, to utilities. I may have my residential building fully functional or my school fully functional, but maybe the transport infrastructure that links those two is not working. And then, of course, with results maybe in displacement of people, as we say in the previous slide, or any other type of education disruption, other type of metrics that, again, may be better, a better way to understand, quantify, and reduce disaster risk. And finally, the final part is hopefully will help introducing Filippo's talk. We have not talked before, so but I know I'm very familiar with Filippo's work, great work, and know I'm pretty sure what he's going to talk about. So in most of the cases, the existing risk models there is a heavy reliance on empirical data, particularly on both on the vulnerability but also on the hazard component. And of course, because empirical data, past observation are a great benchmark that we can use for instance, for validating our models and to calibrate our models, of course. But often, especially when you work in low-income countries, not necessarily have all the amount of data that you actually need. So, and that's particularly an issue in seismic hazard assessment, and within seismic hazard when we are estimating, for instance, the level of ground shaking in a given region using empirical model, ground motion model, regression-based. And so why this is an issue, and this is some work that Karim Tarbali has done with us when he was at UCL, and now I know he's in France. So when we use, for instance, global data sets of ground motions to calibrate some of those models, we have an example of model developed by the Pacific Earthquake Engineering Research Center in California, the NGA West 2008. You can see many events, about 3,000 ground motions, but you see a lack of data, typically high magnitude, close distance type of conditions. And of course, because very strong earthquakes are rare, and that's good, or because you may have issues with sensors in the close proximity of a fault. Then 5 years after, usually there are updates every 5-10 years of those databases. Many more ground motions. We go from 3,000 to 21,000, but still there is a lack, quite a significant lack of events in this region. So it means that when we are calibrating empirical model for those more extreme conditions, which are also those that possibly results in stronger impact and higher losses, we are really missing something. And that's confirmed by the fact that when you look at empirical model over the years, so you can see here number of records, number of data has increased almost exponentially over time. Same in terms of number of models. Everyone has developed GMPs or ground motion model in the last few years, including in our group. But then if you look at the uncertainty around some of those models, there is not really this huge improvement, despite having much larger data sets and more refined models, sometimes very complicated models. And that's because, of course, there is a large variability to the fact that the way in which the source, path, and side effects are represented in those models is very simplified. And so really, there are limitations in the way we can understand. One way to address that, and I hope this will properly introduce Filippo's talk, is to use physics-based hazard modeling. Again, here we are doing that for different type of hazard, not just for earthquake, but for earthquake, the idea is that you can, starting from a fault, you can simulate the rupture, you can simulate the wave propagation. If have a velocity model that gives you information about the properties of the crust, and so in terms of propagation of seismic waves up to the very local site effects. And that's a better way because, of course, you can capture much better, for instance, especially if you are looking at future expansion, urban planning, you want to know at a very fine resolution what is the level of shaking that, for instance, you are expecting, so that, again, you can make more informed decisions. That's key. And again, you will find the other paper, but I'm sure Filippo will discuss a lot around those issues. And also, of course, how those issues together with data-driven approaches and empirical data. So I'm not saying we need to completely throw away all the empirical data and empirical approaches, but together the physics-based models plus empirical approaches can work fairly well. So long story short, there are a number of limitations in those existing risk models. And so what we are trying to do, and you'll see today in those two talks by Filippo and Gemma, and some references here, I know it's a bit advertising our own work, but again, there is a lot going on also from other groups, is really we want to try to address those limitations. And again, the two next talk will show some of those. I'm not sure I've done okay with time. I'm sure I'm done quite badly with time, but hopefully it was interesting enough. Thanks a lot, Marco.
Thank you, Carmine. That's great. Thanks.
Thanks a lot. I'll stop sharing.
Carmine, for this great introductory presentation. I just want to remind all participants that the Q&A session will take place at the end of the final presentation, but feel free to write all of your questions in the chat in the meantime. So our next presenter is Filippo Gatti. Filippo is an assistant professor in mechanics at Centrale Supélec. He's been there since 2019. So he holds a joint PhD in civil engineering from Université Paris-Saclay and from Politecnico di Milano. He has a Master's of Science and a Bachelor in Engineering from Politecnico di Milano. He is currently head of the research operation Hybrid Twins Simulation Learning within the Laboratoire de Mécanique Paris-Saclay, and head of the Master 1 program in geomechanics and constructions. His research focuses on computational earthquake engineering and machine learning applied to civil engineering. So, Filippo, please proceed.
Thank you very much, Reine. Thank you very much, Marco, for having me today. And thanks, Carmine, for the assist. I'll share my screen. I hope you can see that.
Yes.
Yeah.
Okay, thank you very much. So today I'm gonna do a little presentation of what we have been doing in the last maybe 9 to 10 years, and quite recently what we are trying to do and what's under development at the lab. I wanted to, of course, mention my colleagues, Fernando Lopez Caballero and Didier Cloutot, who were also my supervisors, and then our 2 PhD students, Gottfried Jacquet, Fanny Lehmann, that are actually now taking the lead on this kind of technical aspects. And then all my colleagues from Italy who I've been working with and I'm working with right now, that of course are part of these developments too. So, well, a little outline of what I'm going to present. I'll try to first give you an introduction by taking a flashback, so taking you back to time until at least till 2018. And then discuss what's open, what were at the time the open questions, and probably a few of them are still open. And then try to present a few answers to these open questions that we had and we keep on having, unfortunately. So let's start with this flashback to 2018. So here you can see what the main outcome of what we have done in terms of research starting in 2013 up until 2018. So we basically developed a spectral element method code called Cent3D, which is now open source. This code is actually an HPC software that allows us to reproduce complex wave propagation patterns in electroacoustic setups. So here you can see it's a simulation of an earthquake, a potential earthquake occurring at the Volvi site, experimental site in Greece. So you see the epicenter and then the waves that are actually being trapped within the sedimentary basins, the so-called Volvi basin. And this is fully heterogeneous domain. So basically we added small fluctuation, random fluctuations to the geological setup. Of course, it goes without saying that this kind of software can run on any machine, but in order to achieve good results in terms of accuracy and some realism in terms of final results, you need a lot of computational resources. I would say that maybe this one is probably one of the, let's say, of the smallest analysis that we managed to run. It basically took us 62 days on one CPU to run these simulations for 13 by 11 kilometers of width. So this was quite a, let's say, a first essay, but at least we managed to validate the model. Then we can even go bigger, and this is another experimental site still in Greece, the Argostoli site, which is an experimental site that has been chosen in 2014 as a focus for many European projects. Here you can see I had just cut a small piece of earth, a chunk of earth around the Argostoli basin, and also I highlighted the fault plane that starts to slip and the wave then propagates into the ground, reaching up the sedimentary basin when the wave amplifies. In order to run this model, actually, we needed to go a little bigger in terms of computer resources. So we needed basically 3,300 days of CPU on one CPU, of course. But thanks to the HPC setup that we developed, we managed to run it in at least 20 hours wall time. The accuracy of this kind of simulations are right now reaching up to 10, 12 hertz. But as you know better than me, even if the computing codes are, let's say, fast and effective, there is still a problem that if you don't know what to put and how to calibrate these models, those models are basically garbage. So you need good data to constrain your model in order to get out reliable results and therefore perform any other further risk analysis as the ones that Carmine talked about before. So another, just to show that, of course, in terms of accuracy, we can validate different models, and then we have to follow that, to search for a trade-off between the accuracy that we want to reach and let's say the refinement, let's say in terms of the realism and the detail of the prediction that we want for the next steps. So here you can see that actually we tested the same simulation by increasing the accuracy, so the polynomial order of our finite element code, and basically we reach up to a consensus that with the green and the red spectra that we managed to produce, the synthetic spectra, were kind of very close. So we didn't need to let's say we didn't need to make any excessively large simulation if we were let's say good enough with an intermediate degree of accuracy. So these are kind of tests that you want to do in order to assess what is the accuracy of your tool for further analysis, and also in order to compare with the recordings, which are the ground truth to which we have to be faithful to. Here, another example of simulation. This was part of my PhD thesis. Well, what I did is I wanted to study the ground motion, perform some ground motion, 3D ground motion realization around the Kashiwazaki-Kariwa nuclear power plant in Japan. The geology setup was quite complicated, especially because not only there were a lot of side effects, but also there were some kind of let's say folded structure, folded geological structure at an intermediate depth. So between 1 kilometers and 5 kilometers, which is something that in general you tend to disregard when you do like column 1D site analysis or even 2D site analysis. And also when you do seismological analysis at a very large scale, because you prefer to use simply layer cake geological models. And actually what we were able to prove is that the seismic response in terms of spectral acceleration, pseudo-spectral acceleration at the nuclear power plant. So you can see here a small map. Basically, the fact of adding this folded structure, even in a 0.5 Hz accuracy range in terms of simulation, managed to basically increase the ground motion intensity, so the intensity of the shaking, especially at one specific site that eventually happened to be the most damaged one during the 2007 Niigata earthquake. So this partially explains why, except the let's say the local side effects like liquefaction or soil amplification at a very small depth, so between 0 and 100 meters, even the intermediate geological setups can be interesting in terms of focalizing the waves towards specific sites. And this was actually quite clear from the simulation, but we have to go very big in order to see these kind of features. Here another follow-up. So we managed to reproduce, thanks to this preliminary site analysis, so at the scale of a small region, I would say maybe 60 by 60 kilometers. We were even able to integrate the nuclear reactor. That, of course, this was done in joint collaboration with EDF, Électricité de France, in the PhD thesis of Mikhail Kores. And actually, we were able to perform some vulnerability assessment of the nuclear power plant by coupling the structural elements with the spectral element analysis. Also, we did another interesting analysis with at the Cadarache nuclear facilities in a blind framework, because we never observed any target earthquake. Probably the most recent one dates back to 1909, something like that. So it wasn't really recorded. And so then even with the help of Reine, we were able also to couple with another finite element model of the reactor building and perform fault to structure fault to structure interaction. Now, with that being said, we prove somehow that validation of historical earthquake and numerical simulation was not impossible, but still very hard because of the lack of data. And also that when you have a lot of aftershocks, that's better, because aftershocks are easy to use for validation purposes. So you don't have to include also the complexity of the fault. You can do that in another step. But there are still open questions. At least in 2018, we still had these questions. First and foremost, what if multiple geological models were made available? That's most of the times the case, at different scales. What if there are no observation? That's the case of France, because there are very few observations compared to other countries in the world because of the moderate seismicity level. But still, there are critical infrastructures like nuclear power plants that we will love to protect. Also, we focused on Japan because Japan is like California, or like now Turkey and Greece and Italy. There are many countries that have a lot of case study that are very interesting, but the problem is always the fact that switching from a seismic context to another is not linear. It's not that easy. So is an aftershock in Japan a main shock in France? Probably yes. We have to experience that before saying, but it could be. And also another important thing is that, okay, the tool is accurate, but it still demand a lot of computational power in order to achieve good results. And maybe to run 1,000 scenarios, it takes a little longer than expected. So we should be able to improve the accuracy by keeping the prediction as fast as possible. And finally, how to improve the SSI, because even if we were able to couple the let's say the different bricks of the analysis, still there are a lot of let's say there could be some mismatch in terms of propagated waveforms from the fault to the site and then to the finite element model of the nuclear reactor. So in the following, I will try to show you a few answers to a few of those questions, because I don't have time to enter into all the details, and then maybe we can discuss about it if you want. So the first thing that we focused on, it's the dimensionality reduction. This is one of my favorite topic. That's why I wanted to start with this, because the problem is that, as I mentioned, numerical simulations are quite interesting and appealing, even if you need a lot of computational hours, but they are still, let's say, quite cumbersome and time consuming. So during Fanny's Lehman PhD, which is actually ongoing, we focused on another case study of rather interest for France, at least, which is the L'Étail earthquake that occurred in 2019 in southeastern France, and which happened to occur close to a region where there is a lot of industrial activity, so La Vallée du Rhône, which is actually very quite a urban developed area. And also there are a few active faults that are very close to the surface. So in this region, well, we didn't have access to many data, just a rough layer cake geological model, a presumable, let's say, active fault slip patch. So with this small amount of data that we have, we wanted to see if first we could validate the model. And that's actually part of the business when you want to then use this synthetic earthquake engine as a predictor, but also try to make it as fast as possible. So the first thing that we thought is that, well, but if I have several different available geologies, can I encode the response of any geology and, let's say, try to map the geological features with the final numerical result, so with the displacement or the acceleration at the surface? Well, first we tried to do that by just randomly add some fluctuation to the 3 or 4 geological layers that were made available to us, and we obtained very different ground shaking, as you can see in the picture here. So Fanny ran many analyses, and the ground shaking was completely different because of the fact that the layers were not the same, and then we were adding random heterogeneities. So the variability in terms of outcome, it's huge. And it's difficult to treat because of the curse of dimensionality that we all have to deal with. This model plus is very large, so it's 80 by 92 by 79 kilometers. And again, we needed a lot of computational, a lot of CPU time in order to be able to run this. So it's also a cost in terms of amount of money that you have to devote to this kind of simulations. So here we can see that different simulation in the 0.5 hertz in the 0.5 Hz frequency band could provide very different comparisons with the recorded earthquake. And this is part of the vulnerability that Carmine was actually explaining before. And it is not a vulnerability, it is not a variability, sorry, in terms of records, but also in terms of synthetic records because of the variability on the input parameters. So here it looks like it's closer to the recorder, to record the Fourier amplitude. On the right, the fit is not very good. So another interesting feature that we are always checking is how those synthetic results correlate with the or at least how do those results match the GMPs, the ground motion prediction equation, because those are the reference. And so we believe that GMPs and numerical simulations might be used together. So they are complementary tools. And so we want to have some sort of consistency between the two of them, because otherwise there is an error somewhere. In any case, at the end of it, we try to numerically span all the heterogeneity, all the variability of the ground motion and of the geological features. And we performed, actually, Fania was able to realize to create 4,000, now I think probably 40,000, now probably 100,000 heterogeneous geologies. Which means a lot of parameters in terms of curves of dimensionality. So we won't be able to run 40,000 simulation, because if we start now, we won't be finished in 10 years. So instead, we started from the notion of eigengeologies, in order to be able to see if there are a few geologies that can represent most of the, let's say, most of the ground motion, or at least the salient features of the ground motion, and then try to recombine them at the end. This is, of course, the first step. So we did it in two alternative ways. First thing first, we did the so-called principal component analysis on the geological profiles. And we ended up by saying that the PCA provided us a good reconstruction of any geological profile in the database, 3D geological profile in the database, with around 500 eigengeologies. Now, the other thing that we thought is that, well, PCA is fine, but it's still a linear process. So why don't we just use or leverage artificial neural networks in order to add some nonlinearity and discover hidden features that are not, let's say, that are hidden within the PCA coefficients. So we use the classical 3D UNet. So this UNet is like classical neural network. For those that are not familiar with this kind of tools, you basically need to perform several convolution in order to reduce your initial space of data into a reduced manifold, which looks like a barcode. So sparse variables with hopefully Gaussian distribution, and then we get back with the code this code bar, and we go back to the physical space in order to reconstruct the geological layers. The 3D UNet actually requires a lot of parameters, but actually those parameters have basically no physical meaning, and the UNet is very well known for very, very good reconstruction. So you input an image or a 3D geological layer and you output an image. So here you can see that actually when you put one of the realization of your geology, you can reconstruct it with a certain amount of coefficient, the PCA coefficients, or alternately with your 3D UNet, depending on how many coefficients the reconstruction is good or not. Again, if we increase the level of heterogeneities, all of those are random heterogeneities, so we didn't add any bias. The only bias that we had were the layer the layer structure that best fitted the records at the tail. So the results are impressive, but also the interesting thing is that we try to reproduce the ground motion not only not running 40,000 heterogeneous 40,000 runs of our code on different realization of the geological layers, but on the PCA coefficients or on the hidden features of the 3D UNet. And what we actually obtain is a rather good, rather acceptable, of course, not always, not everywhere, but a rather acceptable goodness of fit by comparing the PCA with maybe just 1024 components of the PCA and the whole geological profile. We were able basically to reach a very good agreement. So in reality, what we try to show here is that even if we generate a lot of alternative realization of the geological layers, probably if we select correctly a certain amount of eigen geologies, maybe 1024 eigen geologies, that will be more than enough to explain all the variability of your ground motion. This is still, let's say, our guess. We are trying to prove it because so far we just did it on the geological layer and we propagated the waves. We didn't really map. We are working on it in order to map the geological layer or the geological variability into the variability of the ground motion. And also with the 3D UNet, we achieved very satisfactory results. So this was the first brick because we wanted to understand how many data first we would need to perform those kind of studies and how much would it be possible to replace numerical simulation with artificial intelligence tools. Again, here you can see the comparisons between the simulation, the black trace is the simulation with the full 3D heterogeneous geological layer, and the red one is the simulation on the geology reconstructed with 1024 components of the PCA on the left, or alternatively with the reconstructed profile by the UNet. You can see that actually sometimes it can occur that it is just a mismatch in terms of amplitude, but the phase is good. Other times there is actually a mismatch in terms of phase because probably the reconstruction is not good enough at a certain point, so there is a delay in terms of arrival times. Now, this is part of Fanny's PhD, but then there is another PhD student that I mentioned that is working on another tool still based on AI, mixing AI and numerical simulation, which is called the so-called super resolution earthquake generator, as we wanted to call it. So this is actually, this dates back from a few years ago, because when I was doing my PhD, part of my PhD at Politecnico di Milano, we were developing this ANN2BB tool, which basically was rather naive but very effective tool in order to improve the accuracy of the numerical simulation. In a few words, you can forget about the formulas, I will just explain it. It's quite easy because if you consider the pseudo-spectral acceleration, your numerical simulation can give you a good accuracy in terms of prediction between T star and T infinite. So in other terms, the low frequency part of the ground motion can be predicted by the physics and the numerical simulation with very good accuracy. Now, the problem is that for conceived numerical, this T star usually, let's say, even I love to talk about frequency instead of period. I'm more comfortable with frequencies, but in the 0.5 hertz frequency band, those numerical simulations are quite effective. But the problem is that you know better than me that to conceive earthquake resistant structure, you need to design them in terms of broadband records, broadband input ground motion that goes from 0 to 30 hertz at least. So the first attempt that we make was, okay, let's just try to predict the shorter period ordinates via feeding the multi-perceptron, multi-layer perceptron neural network with the long period ordinates in order to predict these red dots, and then fit the spectrum with classical spectral matching techniques in order to obtain time histories that are broadband time histories, but that they can keep, they are informed by the physics at higher periods. So here is the procedure. We was basically matching the spectrum predicted by the artificial neural network and add random phases in order to improve the quality of our prediction, adding some, let's say, random phases, but with a good amplitude that matches the predicted spectrum at shorter periods. This was good, but of course, and also it proved himself to be very effective because we then improved also the simulation of the critical the earthquake response of critical infrastructure like the reactor building, and we did it by just improving the ground motion at far field with this ANN2BB tool, and then we basically ran the simulation, so the blue spectrum. We added the shorter period ordinates and we get close to the red spectrum, which is the recorded one. And then we inputted this black spectrum into the numerical model of the reactor building, and we shake it. And we obtain a good response in terms of amplitudes or spectral acceleration at this point 7R2, which was recorded that recorded the main shock. Now the second attempt, that is what we are trying to do now. It's based on let's say a rather old artificial intelligence tool called GAN, so generative adversarial neural networks. I wanted just to maybe skip the formulas because I don't have much time to talk about it, but the idea is that we always want to find a generator, so a neural network G, that starting from the numerical simulation X provides you a reliable, realistic Y, or at least a realistic ground motion in a broadband spectrum, 0-30 Hertz, not only in terms of amplitude, as we did for the AN2BB, but also in terms of phase. So here we need to classify and try to basically distinguish between data and generated signals. This is the aim of the GAN. And also we try to constrain this neural network to be able to, if we wanted to go back to the initial simulation, to inform this neural network with the low frequency part of the ground motion X simulated via numerical simulation. I wanted to show you the results because probably are more interesting, and then I'm done, I promise. Okay. It's over. I wanted to show you these results. So here you can see that, sorry, this one. Here you can see that the black time history, it is just the the original time history, okay? So 0-30 Hertz. And the red one, which fits quite good in terms of both amplitude and phase, it is the output of the neural network that was fed with 0.5 Hertz numerical simulation. So we basically filtered the record, the black record in the 0.5 Hertz band. And then we outputted the same record, but without having access to the higher frequency part of the ground motion. So basically the neural network was able to generalize the mapping from low frequency to high frequency and produce broadband realistic ground motion. So now what we are trying to do is that what we love to do would be to also add metadata coming from the GMPs, for instance, in order to modulate this response, the response of the neural network, and to be able to produce even more realistic time histories for the prediction of the earthquake risk, and to improve actually the fidelity of our predictor. I go to the conclusion. I am sorry, I went a little late. Let me just go to the conclusion. Where are they? Sorry, I'm here. So what I try to show here is that first and foremost, the numerical simulations are good, but are cumbersome. So we either try to reduce the dimensionality of the input data and the dimensionality then of the output. And then we try to do some sort of a super resolution earthquake simulation by making up a little the numerical simulation with artificial intelligence tools. Those artificial intelligence tools are actually trained on real records. So they basically learn the low frequency to high frequency map on the records, and then they simply reapply this map to the numerical simulation in the frequency range to which they are made available or they are accurate enough. And so about the perspective, as I mentioned, we want to now run many simulations at a cheap cost by using the metadata, by leveraging the metadata. Thank you very much. I'm on time.
Okay, many thanks, Filippo, for the fascinating presentation. So the final speaker for today's talk is Gemma Cremen, who has been lecturer of risk and resilience engineering within the Department of Civil, Environmental and Geomatic Engineering at UCL since 2021. Gemma's group develops innovative disaster risk management tools that facilitate informed decision-making for safer future societies. She's also a co-I of the 5-year, £20 million GCRF Tomorrow Cities Hub, and also of the 3-year, €8 million Horizon Euro project mediates a multi-hazard and risk-informed system for enhanced local and regional disaster risk management. So I'll hand over to you, Gemma. Thanks.
Thank you, Marco. Hi, everyone, and thanks for the invitation, Marco and Reine. So today I'm going to talk about creating a decision support environment for risk-sensitive, pro-poor urban planning and development of tomorrow's cities. So across the world, our populations are rapidly increasing. Our world is becoming ever more urbanized and interconnected. And all of this is set against the backdrop of unprecedented climate change, meaning that future earthquake risk mitigation planning is a generationally important issue. However, if we look at the current tools that we have at our disposal to try and address this challenge, we find that they are inherently limited. Okay, and Carmine mentioned a lot of these before, but I'll just go through them briefly again. So, our conventional risk assessment approach involves combining information on hazard, exposure, and vulnerability to produce what we would traditionally call risk metrics. But these approaches tend to focus specifically on existing exposure and vulnerability, failing to consider the fact that our populations are increasing and therefore our exposure is dynamic. And also that the vulnerability of engineered structures today is simply not the vulnerability that they will have in the future, given the aging that will happen in between, as well as the fact that we will have new structures over time. And that brings me to the second point, which is that we tend to focus specifically on individual buildings or other assets, failing to consider the fact that our urban expanses are actually systems of interconnected physical and social networks. And then as Carmine talked through, we tend to then characterize risk in terms of very narrow dimensions like economic loss, which simply don't capture the effects of natural hazard events and earthquakes on everybody in society, particularly the poor and the most marginalized, who have the least to lose in terms of economic assets, but the most to lose in terms of well-being. So what our decision support environment does is it sets out to address these specific limitations. We focus on tomorrow's hazard, exposure, and vulnerability. We integrate into our calculations physical and social networks, and then we characterize impacts across an array of different metrics that capture the effects of earthquakes across a broad spectrum of society. Now, I'm not going to go through the framework on the left-hand side in too much detail, but I just want to mention that this is not just another risk assessment framework, okay? We do have a technical core, which is represented by that gray rectangle. where we do our calculations, but importantly, we invite stakeholders into the process. So there's a number of stakeholder engagement points that are represented by that outer blue rectangle. So this is a participatory approach to risk assessment, evaluation, and decision making. So the framework shown on the left-hand side was the original conceptual version of the decision support environment. But what we've done recently is we've set out to translate this conceptual version into an operational version of the framework that we can actually deploy in real cities. So again, this operational version of the framework has a technical core at its center, which allows us to characterize engineering and social impacts. But we have a number of places where stakeholders come into the process and we have decision making associated with them and with the whole process. So at the very beginning of the environment and at the very end of the environment. And we'll go through exactly how those stakeholder engagements happen through a demonstration in some of the following slides. But the important thing to mention is that for the technical calculations within the framework, we use a simulation-based approach, and that allows us to capture uncertainties, not just in vulnerability and in hazard, which is what we would typically do in a conventional risk assessment approach, but we're also able to capture the uncertainty inherent in future exposure. Now, the ultimate output of the whole decision support environment is what we call a visioning scenario with an acceptable level of agreed risk. So a visioning scenario is an urban plan underpinned by a set of policies. And this reflects the fact that the decision support environment is inherently there to facilitate people-centered, future natural hazard, risk-sensitive urban planning. Now, this concept of agreed risk is something that we will go through in later slides, but by the term itself, it's probably obvious that agreed risk is not something that's just simply objectively measured by our typical risk calculations, but it also involves stakeholder involvement in the process. So within the decision support environment, risk is a subjective measurement. It's not an objective measurement, which we would traditionally have, and we'll see how in some of the following slides. Okay, so now that we have a broad sort of idea of what the decision support environment is, let's demonstrate it for a specific case study. So in this case, we're going to use a virtual urban testbed called Futureville. Now, Futureville sits within a 104 kilometer squared physical footprint. And if any of you are familiar with the Centerville virtual testbed that was developed in the US, it uses the same footprint as that virtual testbed, but that's really where the similarities between Futureville and Centerville end. And just before I go into the demonstration, I want to make it clear that yes, we're using a virtual urban testbed for our demonstration, but we could have used a real city, and we have actually demonstrated and applied the decision support environment to Kathmandu recently. Okay, so for the decision support environment, we're inherently focused on the future. What will our future urban extent look like? So in this case, we're going to think about what Futureville might look like in 2050 and run the whole decision support environment process at that time. Now, today we're in 2023, so we're not sure exactly what Futureville will look like in 2050. Perhaps there will be 9,871 households in Futureville. Maybe there'll be 10,383. Maybe there'll be almost 10,500 or just above 10,000. Okay, we simply don't know because we're looking towards the future. But that simulation-based approach that we take within the technical component of the environment allows us to capture and account for these uncertainties in the exposure. Now, it's important to note that, when we're answering this question, we're not just answering this as risk modelers in isolation from everybody, but instead we bring stakeholders into the process to answer this specific question. So local community groups, government representatives can come together and collectively imagine and envision and propose diverse future versions of their city, what exactly they want their city to look like. And that will be reflected in the urban plans that are then brought through the whole rest of the environment. So this bringing together of stakeholders to envision a possible future version of their city is the first step in the decision support environment, which is the future visioning component. So once we have a broad conceptual outline of the future vision for Futureville, the next step involves formalizing this into a geospatial representation, which is the visioning scenario that I mentioned on a previous slide. So the visioning scenario comprises an urban plan and the policies that underpin that urban plan. Now, it's not just any urban plan. Instead, our urban plan contains layers of different spatial databases that capture not just land use information associated with Futureville of 2050, but also very detailed information on each building that will be present in Futureville 2050 and its characteristics, particularly related in this case to its vulnerability to earthquake hazard. We also encompass detailed information on each household that will live within Futureville, as well as each individual that will be a member of each household. And that detailed, rich information that we store within the urban plan allows us to characterize the impacts of the hazard in very detailed ways, which we'll see in a few slides. So we've now characterized our exposure. The next step involves characterizing our hazard. So in this case, we're going to assume a scenario earthquake that occurs 30 kilometers southwest of Futureville, and it's a magnitude 7 event. So we subject the earthquake to the visioning scenario, and the next step involves characterizing the effects of the hazard on the physical environment of the visioning scenario. And we can do this using our conventional approaches like fragility functions and vulnerability models. And again, we're not just focused on individual building assets, we can also incorporate physical networks into this component of the environment. So this is where a traditional risk assessment would stop, but we go one step further by also accounting for societal implications of the damage to the built environment. And we can do this thanks to the rich information on each person we have stored in the visioning scenario. So based on that information, we can tell where each person lives, where each child goes to school, where each worker goes to work, which grocery store each household depends on, for instance. And then depending on the damage to each person's dependent physical environment, we can come up with the effects of the earthquake on society. So now that we've characterized the physical and the social implications of the earthquake for Futureville, the next step involves synthesizing those impacts into what we would traditionally call risk metrics. So we do this as part of a risk agreement process. Now, in this case, for the purposes of the decision support environment, risk metrics are referred to as impact metrics, and you'll see why in a moment. So we bring our results to the stakeholders, and the first question we ask them is, well, what types of impact metrics are important to you? So we're not just characterizing impact and risk in narrow dimensions that have no relevance to the stakeholders of interest. So in this case, we decide, or we assume, that the hypothetical stakeholders of Futureville are interested in mitigating population displacement as a result of the earthquake event. So in this case, we're assuming population displacement is a function of damage to residences, schools, workplaces, and stores within Futureville, given the fact that we know which of these buildings each person within Futureville depends on, and the fact that if there is damage to these important buildings, people are likely to leave Futureville as a result. And we also assume that they're interested in minimizing the disproportionate extent of residential damage experienced by low-income groups. Now, an important feature of this impact metric is that we're disaggregating an impact by income group. And we're able to do this given the rich information that we've stored on each person within the visioning scenario. So we can tell what income group each person belongs to, and therefore understand which households are low income and which of those households have experienced residential damage. We also ask stakeholders to determine the relative importance of each of the impact metrics. So in this case, the stakeholders assume or tell us that both of the impact metrics are equally important. Now, it's the objective magnitudes of the impacts combined with the subjective preferences or priorities that the stakeholders place on the impact metrics that collectively characterize risk within the decision support environment. So as I mentioned before, risk is a subjective measurement here that really brings stakeholders into the process, allowing stakeholders to have ownership over the whole process. And risk is a function then of what we would traditionally call risk, but in this case is called impacts. They're the objective measurements of the effects of the earthquakes on society, and we combine them with the subjective preferences of stakeholders to come up with risk. Okay, so now we have risk defined for our case. The next step involves assessing different visioning scenarios to determine the final output of the decision support environment, which is that this visioning scenario with an acceptable level of agreed risk. So in this case, what we're going to do is we're going to keep the urban plan constant, but we're going to change the policies that underpin the urban plan. And by changing those policies, we're changing the overall visioning scenario. So in this case, we're going to examine 3 visioning scenarios in particular. The first one has a policy of replacing all buildings in low-income zones with higher code buildings. The second policy focuses on future development in particular and regulates and stipulates that that future development should be built to a higher code than existing urban development. And then the third policy is a soft policy, which involves issuing financial assistance to those who are affected by unemployment and residential damage as a result of the earthquake. Now, each of these policies will have different influences on the underlying impact metrics that we characterize. And we can represent these differing effects on the impact metrics through plots like this. So straight off, we can see that policy 3 leads to the lowest level of population displacement, but policy 1 reduces the disproportionate effects of residential damage on low-income populations. Now, this first initial finding underlines the importance of characterizing the effects of the earthquakes in terms of multiple dimensions, not just focusing on a single dimension. And then as part of the visioning scenario assessment, which is really the last step in the decision support environment, we combine those objective measurements of impacts shown in the graph with the subjective priorities of stakeholders towards each of the impact metrics, which in this case is an equal importance placed on both impact metrics to determine the best visioning scenario, the ultimate output of the environment, which in this case we find to be policy 1, a hard policy of replacing all buildings within low-income zones with high-code buildings. Okay, but what would have happened if instead, during the risk agreement process, the stakeholders identified the same impact metrics as being important, but they placed a much higher emphasis on reducing population displacement then reducing the disproportionate consequences of residential damage on low-income groups. Now, if we ran through the whole process again with our different visioning scenarios, of course, our objective impact metrics wouldn't change in value, but we would have to then consider the differing relative importance that stakeholders place on the impact metrics when ultimately characterizing risk. So in this case, instead of policy 1 being the best policy, actually policy 3 would have been the best policy. And this makes sense because policy 3 ultimately leads to the lowest amount of population displacement, and population displacement is heavily prioritized by the stakeholders in this case. So this was quite a straightforward, simplistic demonstration of the decision support environment, but it nevertheless emphasizes the importance of engaging the stakeholders in the process, because the stakeholders' preferences and priorities towards the impact metrics can ultimately change the visioning scenario, the optimum visioning scenario to be chosen as a final output of the whole decision support environment. So in conclusion, we've presented the Tomorrow Cities decision support environment, an end-to-end stakeholder-driven process for modeling, characterizing, and assessing risks associated with future earthquakes. The technical core of the framework overcomes a number of limitations of existing conventional risk assessment approaches. We focus on tomorrow's exposure, vulnerability, and hazard, and we integrate approaches into our methods in order to facilitate this consideration. We account not just for physical impacts, but also social impacts and social interdependencies with physical assets and physical networks. And we end up characterizing impacts in terms of a number of dimensions, and we ultimately subjectify risk, inviting stakeholders into the process to make the whole process inherently participatory in nature. We then demonstrated the whole TCDSE, as we call it for short, using the Futureville case study. And this was a very straightforward, simplistic case study just for this presentation, but it nevertheless emphasized the importance of the stakeholder engagement process in the whole decision support process for future urban planning. Okay, so we have two QR codes shown on the bottom left of the screen. One points to an Earth's Future paper, which was the original paper we developed on the decision support environment. And then the second QR code points to a special issue on the decision support environment, which was also highlighted by Carmine at the very beginning of the presentation. So that is in the works. We have a number of papers published within the special issue, but we will have a number of more papers published in due course. Thank you very much for listening.
And thank you very much for your presentation, Gemma. And before opening the Q&A, I would like to thank all the speakers for their great presentations. I think they presented very stimulating research projects and case studies, and it's not just by chance they attracted more than 120 people today joining this call. So now we can move to the Q&A session. I think there are already some questions in the chat, so maybe we can start from the question by Luca Lombardi to Carmine, who was asking for an opinion on current approaches in multi-hazard risk modeling.
Yep, thanks Marco, and thanks Luca for the question. Yeah, it's something I didn't stress enough because of time, of course, because the webinar today is more focused on earthquake. So current approaches in multi-hazard, unfortunately, I think they fail in addressing multi-hazard in the sense that often they look at individual hazards, and what they try to do, they try somehow to combine what Gemma called the impact matrix, the loss. And I think what is missing there is the fact that hazard can interact. And can interact in two ways. Of course, we are all familiar with some of the cascading hazards coming from earthquake, for instance, liquefaction, tsunami, landslide, and so on. But something that I think is even more interesting is actually what in the literature is called level 2 interaction, where the interaction happens not necessarily because of the hazard, but also because of the impact What I mean, again, a simple case for earthquake is where you have a sequence of aftershock, you have the main shock, the building is damaged, there is a reduced capacity, and then the effect of a second shock, that can be an aftershock, can be a triggered event on a nearby fault, is actually higher because of that reduced capacity due to first shock. But even, two others can be completely independent. Imagine there is an earthquake today, and it actually happened in Turkey. We had an earthquake a few weeks ago, and then a few days ago there was a strong flood. So those events are clearly independent. There are no interaction from the other point of view. But because you are still in the phase where essentially your asset or your community, we can look at a different scale, is recovering from the first event, essentially, there is again some cascading impact, some cascading consequences that actually are worse. So your functionality, for instance, will be made even worse because of the second event. So what we are trying to do within our group, Kenneth, who is here in the chat, one of the PhD students, is specifically with Leandro, the two of them are focusing, research fellow working in our group, they are focusing specifically on this problem. We look at the idea of life cycle consequence analysis. So the idea, look at an asset for, let's say, 50 years, can be an event time frame. And that 50 years, you can simulate different events that can be independent, can be correlated, because again, they are cascading, or maybe, it's an hurricane that is producing wind, strong wind, plus flood, plus sea, coastal flood, rain. And then we compute the consequences accounting for that. But what is also important to model the recovery between two events, because you may have repair if the events are, far in time. I mean, they are not so close in time. But in parallel, you also have deterioration, because we have stressed a lot today, there is aging, because, climate change may make some of those. So I think really you need to look again at this idea of, and I think we've been working on many of those existing frameworks for multi-hazard. Many of them are very qualitative, or they pretty much just focus on the first level of interaction, the quite obvious one. Or sometimes, they look at very extreme cases. Yeah, there is an earthquake here that will trigger a flood like 200 kilometers. I mean, I think the idea is instead to look more at this idea of, damage accumulation and propagation and accumulation of consequences because of different type of hazard that can affect the same asset in a given time frame. Look, I hope that makes sense and that it make you more confused than before.
Thank you, Carmine.
Thanks.
Thanks. There are a few questions that somehow have been addressed already by our speakers. Maybe I'll pick one for Filippo, then maybe can expand a little bit, maybe a question that others have asked themselves. So from Mahir Setin, there is a question about how does using some of the eigen geologies reduce the computational time? So does it reduce the number of degrees of freedom on the model? So maybe that's a question I think you may want to just expand on this, Filippo. Or,
yeah, sure. Thanks for the question. I tried also to answer in the chat. It does not. Well, first and foremost, it depends on how you compute the degrees of freedom, but eventually the degrees of freedom as we do compute them is just the same. That depends only on the mesh of your model, and we don't change that. Mesh is the same. It could be different in terms of accuracy because actually the amount of the distribution of velocity, or let's say the mechanical properties, in order to be more consistent, of each eigengeology is not the same because the geologies are different. Of course, we tailor the mesh in order to be as much accurate as possible, and then we keep it. We fix it. What we just do is that what Fanny does actually is that she just compute an earthquake. So she does run an earthquake analysis for a PCA coefficient. But now what we are trying to do is we are trying to match eigengeologies with the eigen scenarios, if we love to call, because we know that for every eigengeology, basically what you have is a green function. If you consider one point source, then there is the fault thing, but I don't want to enter into this intricate topic. And so the thing is that we would love to be able to have a neural network at the end, or whatever the AI tool could be used, but that matches immediately whatever the geology to whatever the scenario, because we are able to map the uncertainty of the geological layers, the uncertainty of the geological setup, to the uncertainty of the response. And then also, if we manage to do that, we'll also take care of the position of the source, at least. It's still elasticity, so we are not entering the nonlinear world for the moment because it's too cumbersome. But at least what we love to be able at the end to have is to basically have a neural network that if you provide any geology, the geology can basically be decomposed into its PCA coefficient if the database is large enough. And so the network has learned in a hierarchical way how to match every eigengeology to a certain scenario, a certain response, a certain green function. And so it can map directly the scenario, or at least a prediction of the scenario, without running any simulation. Even for geologists that had never been seen.
See, I think that was a very good response. I hope people can also, if they want to interact with the speaker, can also open their mic and sort of provide more questions. But I think, yeah, got your response. And there's a question for Gemma about risk development policy. The question from Richard is that going to involve government, or depends on the client, or probably which are the stakeholders?
Yeah, thanks, Marco. Thanks, Richard. So the idea is that the environment is there to support decision making rather than to make the decisions. So yes, policy will ultimately be implemented by the government, but the idea of the decision support environment is to bring people together to understand the implications of different policies, so they can then make the right decisions around policy making. So we're not there to say, this is the best policy that you could possibly ever implement. It's more saying, these are the sets of policies available to you, and this is the one that would lead to the lowest level of risk that's sort of been agreed by everybody in the room as to how important the different impacts are. So the different types of stakeholders could be, very, very different groups, and ultimately the policies that are implemented are controlled by, one of those groups. But the idea is to just get everybody participating to support the best decisions that could be made. So the stakeholders could be, for instance, local community groups. They could be, charity representatives. They could be government representatives, members of civil defense, for example. So very different groups that all really ultimately are influenced by urban planning decisions.
That's great. Thanks, Gemma. There was more a comment rather than a question, or sort of asking someone from, I think, the Middle East or Pakistan, asking whether we can provide some advice to get more into these topics. Of course, one advice we can give as young members of our society is to look at the presentations that are available on the YouTube channel, for instance. Is a good start to have maybe a wide range of topics that deal with risk and earthquake risk from different angles. I think an example has been also this presentation today that has dealt with the topic, looking at different case studies and also different components of what then makes risk. So I don't see any further questions for the speakers. So as we're reaching the end of the seminar, we would like to actually make a small announcement about a future initiative that our societies would like to propose and see. So I may let Reine to say a bit more about it. And I'm going to share maybe my screen.
Yeah, well, I would like to thank again Carmine and Gemma and Filippo for the presentations. Well, I have prepared a paper full of questions, but I think we will not have the time to tackle that. So I hope everyone has learned something today. So this was our first joint event with the SECED, and I was happily been the co-chair of this event. So what's next, right? Okay, so how about a joint workshop in the UK in 2024? So this is an idea. we are open to all ideas, so you can send us an email or write us something. So we thought about that because in France, well, we do already technical days. In the UK, the SECED that doesn't do apparently technical days, so we can like put our minds together and maybe do something for 2024. So if you can please scan this QR code and let us know if you would like to participate, if this seems a good idea to you. And well, yes, so please take some time just to scan this QR code and give us your answer. I already see that some have started to respond. But yes, feel free also to write in the comment what do you expect from our both youth groups to do next, and well, what would you hope to the topics maybe to hear about for the next seminars? Yeah, please feel free to write something. I don't know if Marco wants to add.
Yeah, that's definitely like to bring more opportunities for our members to network also between, not just within our two countries, but also across the two countries. And I think that would be great. So while people maybe are giving their answers, I would like to thank again our speakers and everybody that has joined today. So we had very good attendance and also good Q&A session. So you can find a recording, or we will be finding a recording of this seminar shortly on YouTube. So all the links that our speakers have shared, and also the QR code at the end of this presentation will be available again. So hopefully everything is going to be still available for you to provide your feedback and or send any questions to our speakers that you may not have had the time to put in the chat yet. So I believe with this, we can probably close our seminar today. I would thank you again, everybody, and see you at the next second or FFS event. And yeah, thank you very much.
Yes, thank you very much.
Thank you.
Thank you. Bye.
Thanks everyone, and Marco and Reine for
Bye.
this.
Bye.
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 Bye.